So I heard this great story the other day. It's actually about a little boy who had gotten a pet. True story. Gotten a pet lobster in his fish tank, and one day his mother realized that the lobster was just going crazy. It was just like darting around the tank and trying to run into the fish and trying to grab the fish and climbing its way up the filter and all of this stuff. And she finally realized that the lobster was actually starving to death because lobsters need to be fed about 4 times a day, and her son was feeding it about once a day. So you're thinking, what does this have to do at all with biochemistry? Well, it really does, because phosphoarginine is the high energy phosphagen in the muscle of lobster tissue.
I thought it might interest others of you who have interest in athletics, who are elite athletes or coaches, to know that phosphoarginine in the skeletal muscles of lobster is actually analogous to phosphocreatine in our skeletal muscle. That probably rings a bell because phosphocreatine is a high energy phosphate store that we can tap into to power outbursts of energy. Therefore, it's very popular and famous within the world, primarily of weightlifters, and they try to supplement with oral creatine. And what's actually really kind of interesting about this, and I'm going to bring up a site that we can maybe assess for fun about creatine and phosphocreatine. And to think about the fact that this really relates awesomely to our current coverage of mass action ratio, because as it turns out, in oral supplementation of creatine, what athletes are trying to do is to allow that mass action ratio to be in favor of the creation of phosphocreatine in vivo. So by taking in extra creatine in the diet, the hope is to create a high concentration of reactants in this reaction here, whereby creatine reacts with ATP to form phosphocreatine and to create a higher store of phosphocreatine, that high energy phosphagen. So once again, trying to create a concentration of reactants that is higher than products and to have a favorable mass action ratio for the creation of phosphocreatine. So it would be fun, wouldn't it, to get a copy of Creatine, a practical guide, and do a little source assessment on that.
So phosphoarginine within lobster muscle is such a high energy molecule, and this is actually a picture of phosphoarginine right here. And what you notice is that it does have a high energy phosphoryl group on it. And this high energy phosphoryl group can actually be transferred to ADP to make ATP. We'll look a little closer at that type of a transfer later, but it can be transferred to ADP and it makes ATP for short bursts of energy, and so it can actually be tapped into to provide for around those sort of 10-second or less bursts of energy, that 9-second or less really, that can be allowed from your high energy phosphagen stores. So in a lobster muscle, this is the molecule that makes that possible. So what we've written down then here is the reaction that we know then must be very exergonic because it can make ATP of phosphoarginine losing its high energy phosphate, forming arginine and an inorganic phosphate. Delta G naught prime tabulated value for this is negative 32 kilojoules per mole. So indeed it is highly exergonic, spontaneous process. And we see that this tabulated value kind of gives that away, at least at standard state. But we also know that it's the actual delta G that we want to look at. So the goal then for the first part of this question is to answer this. What is the delta G in resting lobster muscle? So we want to know what is the actual delta G, that being the major difference, the actual as compared to the biological standard state. So we know that the equation that we're going to need to use then is this one. Delta G is equal to delta G naught prime, and of course plus RT, the natural log of products over reactants. Let's go ahead and insert the actual products over reactants. So arginine, concentration arginine times the concentration of inorganic phosphate divided by the concentration of phosphoarginine. Okay, so that's the equation we know we're going to need to use. However, obviously we need to be given a little bit more information before we can do that. We've been given the delta G naught prime, so we know we can plug that in right there. So that's good. But we also must need to know something about the concentrations of arginine, inorganic phosphate, and phosphoarginine within the resting lobster muscle cell. And in fact, those values are given in this question, and I'm going to erase the structure of phosphoarginine so that we can write down those given values. So those values are concentration of arginine equal to 2.6 millimolar. Concentration of inorganic phosphate is 5 millimolar. Concentration of phosphoarginine that is equal to 6 millimolar. And that helps us with that, but we need one other thing, don't we? Temperature. So the temperature is going to be 25 degrees Celsius. And I'm not sure if that's an accurate temperature assumption. This is the temperature given in the problem, but I would say that we would vary there with the terms of the temperature of the actual lobster muscle. But let's convert this, we know, to Kelvin, because in this equation we'll always work with the absolute temperature in Kelvin. So remember that Kelvin is equal to the degrees Celsius plus 273.15, and we could plug in then for that and just simply go ahead and get that calculated, knowing that the Kelvin temperature is 25 plus 273.15, which is actually going to give us Kelvin temperature of 298.15. Alright, I think we have all the information that we now need. Now, one thing though to be careful about is remember your units. So R, if we remember back to that constant, is in joules per Kelvin mole. So remember, everything's kind of got to go around that. So that R value is going to, we'll go ahead and plug that in. We want to get the delta G, the actual delta G. So if R is in 8.315 joules per Kelvin mole, everything else needs to be in joules and degrees Kelvin. We already did the conversion for the temperature, but notice this is in kilojoules. So a quick conversion from kilojoules to joules takes us to negative 32,000 joules per mole. So important that we watch those units. That looks good. And then we'll plug in for temperature, 298.15 Kelvin. Okay. And then the natural log, and we're going to have these actual concentrations in here now, all in millimolar. So hang on a minute, we're going to need to be in molar. So let's go ahead and transfer those to molar concentrations. 2.6 times 10 to the minus third molar. Oh boy, just running out of room there. Let me put in the bottom one, divided by 6.0 times 10 to the minus third molar. and needing to be inserted right there, since I ran out of room, I'll just put it here. We would have the 5.0 times 10 to the minus third molar. So that's going to be inserted right in there. So those concentrations then just converted from millimolar to molar and inserted in our equation. And so we end up then with delta G being equal to, and if you just want to plug and chug that through your calculator, you can go ahead and plug those in. Don't forget to take the natural log of this entire term. Okay, and it looks like we get delta G is negative 48,000 joules per mole. Or if we wanted to go ahead and put that in kilojoules per mole, we could say that that is negative 48 kilojoules per mole. Cool, hey, check that out. That totally means that the reaction is actually more spontaneous, more exergonic in actuality than the free standard state value tells us. So negative 48 kilojoules per mole as opposed to the negative 32 kilojoules per mole. Hey, so we definitely can see that delta G and delta G naught prime differ from one another, and certainly that delta G and delta G naught prime are not the same. So let's ask ourselves the next question, right? And that is this reaction of phosphoarginine going to arginine plus inorganic phosphate, is it near equilibrium? That is KEQ close to Q? Or is this a metabolically irreversible reaction where KEQ differs from Q by 2 or more orders of magnitude? So let's plug in and find that out next. Is this a near equilibrium? Or metabolically irreversible reaction? That's what we want to know. Okay, so how much does KEQ differ from Q? So first we have to get KEQ, right? And we know that KEQ relates to the delta G naught prime by this equation. Ten raised to the delta G naught prime divided by 2.303 RT. So KEQ 10 to the negative 32,000 joule per mole hey, look, I forgot a negative sign. Negative, and that makes this negative negative, which we know is going to put our equilibrium constant lying with the products greater than 1, which we know it does lie with the products, right? Okay, cool. Spontaneous, exergonic. 2.303 times 8.315 joules per Kelvin mole times 298.15 Kelvin. Ooh, sweet. Little unit canceling that can go on there. Kelvin. And we find out then that KEQ, plug that in your calculator. Well, we know it's going to be positive, greater than 1, right? Lies with the products. 4.025 times 10 to the 5th. Cool. So that's our KQ, but now we need to know, well, how does that compare to Q? Because that's what will allow us to answer this question. So let's find out what Q is. Remember, Q is just that mass-action ratio, and in fact we already sort of calculated Q and took its log in the last equation because it's just products over reactants. So it's just the concentration of arginine times inorganic phosphate divided by phosphoarginine. And so that is going to be 2.6 times 10 to the minus third times 5.0 times 10 to the minus third divided by 6.0 times 10 to the minus third. Remember, those are just the millimolar concentrations that were given, and then that allows us to get Q, and it looks like Q equals 2.17 times 10 to the minus third. Gosh. Hopefully you guys can read that. 2.17 times 10 to the minus third. So look at the difference there between KEQ and Q. Is that more than 2 orders of magnitude? You bet it is. This reaction is definitely metabolically irreversible. Now within metabolism, we are going to see some reactions that are near equilibrium and some reactions that are metabolically irreversible. Now you'll understand what makes them so. Now when we think about it, where would be a better point to regulate? Would it be better to regulate at a reaction that was near equilibrium, or would it be better to regulate metabolism, have an enzyme that is subject to regulation at a metabolically irreversible step? I want you to think that through.